All right, good evening, everybody. I'm going to talk a little bit tonight about the Charles Law Lab that you're going to do. For this particular unit, I have been having you do, and I will continue to have you do some labs before we actually talk about the laws themselves. I'm hoping that before we talk about the laws, you can see what happened in the lab and then go back. And once we teach you specifically about the laws and look back and be like, oh, yeah, we saw that in the lab. Oh, right. I remember seeing that. So I'm going to talk a little bit about Charles' Law, but we're really going to see what happens in the lab, do a lab, and then we'll talk more about the details of it later. But one thing I did want to start with really quickly was talking about temperature. In particular, I want to be able to talk about the Kelvin and the Celsius scale and the difference between the two. So, a couple things to understand about temperature. In modern times, chemists have their big theory, and this is called the kinetic molecular theory, and you should already be familiar with it. It's the idea that the average kinetic energy of gas particles, or in other words, their motion, is proportional to the temperature of the gas. So as the temperature increases, the motion of the molecules increases. As the temperature decreases, the motion of the molecules decreases, or particles. It doesn't even have to be molecules. Molecules move faster in warmer temperatures and exert a greater pressure. That's going to come into play in just a minute. They exert a greater pressure on their containers when they're moving faster. So we would experience higher pressure in warmer temperatures. In 1848, now I'm going back in time, there was a fabulous British gentleman named Lord Kelvin who suggested that if we use, I think the word he used was gradations, maybe it was graduations, that's what it was, graduations. If you follow backwards this pressure and temperature idea and the motion of the molecules idea, he said there must be a lower limit to temperature. There must be a point where temperature can't get any colder. And he said that if things got cold enough, the volume of air must drop to nothing. And we've been trying to prove that ever since. So he was the one that proposed what we call now today the Kelvin temperature scale. And on the Kelvin temperature scale, the number zero is absolute zero. Absolute zero is the idea where basically motion stops, where the molecules stop moving, because temperature is basically a measure of motion. The more motion there is, the higher the temperature is. So theoretically, if there's no motion, there's no heat, there's no temperature. So we think it is impossible at this time, like traveling the speed of light, we think is impossible. At this time, we think it's impossible to actually achieve absolute zero. Theoretically, absolute zero, if we were to achieve absolute zero, it would lead to the collapse of the atom because those electrons are traveling around the nucleus. They would collapse into the nucleus, and all matter would collapse. And so we think that absolute zero is only theoretical and not actually something we can ever achieve. But we've gotten wickedly close to absolute zero, but we haven't quite met it. So now let me tell you a couple other things about the Kelvin and the Celsius scale. The way that Lord Kelvin set up his scale, he said that each step on the scale was equivalent to 1 degree Celsius. However, the Kelvin scale doesn't use the term degrees. So when I write 60 degrees Celsius, I have that little degree sign. But if it is 273 Kelvin, I don't put any kind of a degree sign. There's also no negative numbers in Kelvin. The lowest temperature that is possible is zero. That's absolute zero. You can never get colder than that. So there are no negative numbers. You need to understand how to convert between Kelvin and Celsius. It's a super easy conversion because the steps are the same size, because 1 degree Celsius is equal to one step on the Kelvin scale. So all you need to do is add 273 to the Celsius scale, to the Celsius number, and you have it in Kelvin. So for example, if our temperature is 20 degrees Celsius, then we do 273 plus 20 degrees Celsius to get 293 Kelvin. I can do that math in my head. And vice versa, if we were to go the opposite direction, if we wanted to go from Kelvin to Celsius, we just subtract 273. So if the temperature was if the temperature was 293 Kelvin, we would subtract 273 from it to get 20 degrees Celsius. All right, so now my dog is sneezing in the background, pardon me. Now I'm going to have you do some kind of wacky stuff. I'm going to ask you to pause this video, but don't close it. Open a new tab and go to the other video that should be linked on Classroom. Now, this is a laboratory video. It's done by the North Carolina, let me see if I can remember the whole name. It's like the North Carolina School of Science and Mathematics. I think that's the name of the school. Anyway, it's just a 3.5 minute video, but they're going to do a lab. So you need to open that video and watch that video. And you need a third tab open to the Charles Law Lab worksheet, and you're going to fill in the worksheet as the lab is going on. So you might need to pause that video a couple of times so that you can add data into your data table for your Charles Law Lab. Once you have watched the whole video and your data table is complete, then come back to this video and I will start a discussion of how to finish the data and how to finish the graph for the Charles Law Lab. So I'm going to pause for a moment and then I'm just going to continue on. So if you don't pause, I'm going to jump right into the graphing as though you have watched the video and filled in your worksheet. So I'm going to pause right now. I'm waiting for you to pause. Pause, go away, go watch that video. Okay, I'm going to assume that you have watched that video and I'm going to go ahead and start up now. So this is the video, by the way. I've got it right here. This is the video that you should have watched all of. So now what I'm going to pull up is the graph of the data. So if I look, let's see, I'm going to try to remember how to do this. This is a fairly new graphing program for me. It's called the Veneer Graphical Analysis. It's kind of this, let's see, I'm going to try to move things around. Can I make it bigger? That's about as big as I can make it. Okay, I think that I can... There we go. I just want to look at the table. So what I did is I entered in the data that they gave you in that lab. And I want to say a couple things that are super wickedly important. In the laboratory, our thermometers are gradated or they use the Celsius scale. So the measurements in this lab are all in Celsius. However, if you're going to do calculations using what's called Charles' Law, which you haven't learned yet, if you're going to use calculations for Charles' Law, you must use the Kelvin scale. I'll explain why you can use Celsius and then we'll go back to the Kelvin scale. So here you can use Celsius because all you are doing is taking measurements in the laboratory and you're not doing any math with them. But the moment that you use Charles' Law to predict the volume or the temperature, then you have to use Kelvin. And let me explain why. Somebody else explained this to me, and I thought it was such a good explanation. I'm going to move this over. I thought this was a really good explanation. So if you go from 20 degrees Celsius to 40 degrees Celsius, you have in effect doubled the temperature. But in Kelvin, that same 20 degrees would be a movement from 273 to 293. That's not doubling. So we have to be consistent. When we're doing our math, the calculations, we have to always use the same numbers. And so we have to use the same scale, and we're going to be using Kelvin. So that'll be important in just a second. So right now, the temperatures that you see and the temperatures that were given in the lab, they were in Celsius, but that's because they're just points that we're plotting and we're not doing any math with them. In just a moment, I'm going to use Kelvin over where it says fake data. So what I did is the temperature of 100 degrees in that first flask that we saw him working with, the volume was 138 milliliters when he put the stopper in. Then when we cooled the temperature down, the molecules weren't moving as fast. They were moving more slowly. They exerted less pressure. And so the gas condensed and we had a smaller volume. So now the volume was down to 111 milliliters in that first flask. Let's do it again. I'll just say it again. He gave us, the rest of them, he just gave us, but we didn't get to see this. So in the larger flask, in a 250 ml flask, we saw, just so you know, a 250 ml flask, the last mark on it is here, but then the neck of the flask goes up. So you can actually add more water into a 250 ml flask than 250 mils. So the full amount of the flask with the stopper in was 255 mils. So that's how much gas was in the flask when it was in the boiling water. And then we turn it over and we put it in the cool water. The molecules of the gas cool down. They stop moving around so much. They exert less pressure, so the water starts seeping in, and the gas has less volume. So the second volume was 208. Same thing here. Notice the first volume is lots of volume because the molecules are moving around a lot, and then less volume because the molecules are not moving around as much, and so forth and so on. All right, so now what I'm going to do is I'm going to take that data. I think this is the right way to do this. And I am going to show it to you. I'll try to get my picture out of the way. So this is the data that I graphed, and you have a graph on your worksheet that looks very similar. Notice the dark line on your own graph on the worksheet. Notice that I gave you a dark line right here. That is to represent 0. Super important. Don't miss this. Right now, in fact, go to your worksheet, and where the dark line is coming down, label that 0 so that you remember. And then going across, we're going to have, so going up and down, that's our volume. That's going to be the volume. And then going across is going to be the temperature. On the x-axis, we're going to start at minus 400, although we could probably, yeah, minus 400 is probably good. And then goes all the way on the right, we go all the way up to a positive 100. Now, again, we're on the Celsius scale, and that works for this lab because we're not doing any calculations. Okay, so then what I did is I asked the computer to graph the 2 points that we were given for each of the flasks. So here's flask number 1. It was the 125 milliliter flask, the one that you actually got to watch. This point right here is on 100 degrees. There, it's 100 degrees, and it's at 138 mil. Oops, sorry. Wrong one. I'm looking at the wrong one. Blue line. The red line is the one that represents that 125 mil flask. Sorry. So here's the point at 100 degrees. And if we scoot all the way over across, that would be where 138 mils would be. So that's the first point, is right there. And then the second point is 23 by 111, and 23 degrees would be right here. So 23 degrees and 111 is about halfway up there. So that's the first line. We made a line between those first 2 points. Then we did each one of the flasks, and each one of the flasks is represented by a different color line. So I'm going to keep going. Here's the 500 ml flask. I wish they were labeled. That would have kept me from screwing up the first time. And here's the 1000. Now here's the fun part. This is such a cool part about this lab, is that it works pretty well. It's not perfect, but it works pretty well. So I'm going to do something here, down here. I'm going to apply a linear fit and hit this. And I want you to see what we did. I basically extrapolated. I continued those lines on. And the question is, if we continued those lines on, what would happen as the temperature is getting lower? The volume would start getting lower also. And if you notice, they all start to point in almost the exact same point. Not exactly, it's not a perfect lab, but it's pretty good. So you see, and you need to look closely, because one of the questions on the worksheet asks for the range of points on the x-axis. I'm circling them right now, where the lines are meeting. So what's the range of, so I would say, for example, this red line, I would say it's at about, if this is minus 250 and this is 300, minus 275 would be right in the middle. So I'd say, what, 290, something like that. That's a minus 290 right there. So your range would be minus 290 to minus whatever. You figure that out on your own. You're capable of that. All right, so now those are the actual lab results that we got. But I thought, well, could we show this with theoretical data? So I actually messed with Charles' law, because I know what Charles' law is. You guys don't. I messed around with some numbers, and I made up my own fake data. So if the temperature had been 100 degrees, and yes, I converted into Kelvin and then back into Celsius again so that I could make this data work. So this is the data I came up with. If I had a much larger beaker than they used, let's say the volume at boiling was 2,100 milliliters. And then the volume at 23 degrees was 1666. I'm gonna go crazy on sig figs here, just so we can be as precise as possible here. So 1666.4879. And I'm going to ask it. Oh, I hope I can do this correctly. I'm going to ask it to graph it, and suddenly I forgot how to make it graph it. Uh-oh, please graph it for me. I don't remember how to make a graph. Oh, there. Phew, I was worried. So this is my fake data that I tried to make it as precise as possible. So I used a much larger beaker, fake beaker, and I gave you this data right here. So this was the original line right here. This is the first point at 100 degrees. This is the second point at 23 degrees. It was a bigger beaker. But notice that if we extrapolate and we keep following that line down, we land at almost exactly a minus 273 degrees Celsius, which is absolute zero. So absolute zero on the Kelvin scale is zero, and absolute zero on the Celsius scale is minus 273.15 or something weird like that. So I'm showing you that that's what the point is here on the Celsius scale. And so Charles' law is able to predict that absolute value should be at this particular spot on the temperature scale. All right, trying to think if there's anything else we need to know. You've seen the graph. You need to make the graph yourself. So I'm going to pull this up. Here's the graph. Let's see if I can make that bigger for you. This is the graph that you're going to make yourself. So here's your zero line. Here's your temperature line, and I give you a little hint. I say you don't need to number every single line. I don't need you to write a million numbers. You could, be skipping some numbers, but you have to maintain even increments. If you go by 100, so if each of these lines is 100, so for example, if this was 0, 100, 200, 300, 400, 500, 600, and so forth, that should work. And then if you went by 50s on the horizontal, so this is 0, so this would be a positive 50 and a positive 100 degrees Celsius. And if you went backwards this way, it would be minus 50 Celsius, minus 100 Celsius, so forth and so on. You should be able to make that graph yourself now based on the graph. And rewatch this video if you need to, back up and look at my graph if you need a little help. Did you remember to title your graph and to add labels and units? Because that's for sure something I'm going to be checking for. And then you have questions that you need to answer. And then finally, at the very ending, you need to decide which equation is the correct equation. Now, you could totally cheat and look it up, but it ruins kind of the fun or the purpose of what we're trying to do here. The one thing that is important, it says for these calculations, you must convert temperature to the Kelvin scale. So I said that this is 100 degrees Celsius. So how do you convert that to Kelvin? It's really simple. How do you convert that to Kelvin? Add 273. Okay, so just add 273 to those, and then you can use them in these calculations. So see if you can figure out what the right equation is for Charles' law. I guess that's it, everybody. Have a good night. Thanks.